Sometimes we have to solve problems involving variables that we know there's some kind of relationship between them, but we're not necessarily 100% sure what that relationship is. Now, regression analysis cares about solving these types of problems. Regression analysis in particular is looking at finding the best model of that relationship. Now, if the relationship is exact, that is, like, there's no fuzziness at all involved, then that relationship between the variables is considered deterministic. And the whole venture to find the best model of that relationship is really kind of boring. So we're just not going to deal with that. Regression analysis that we're going to talk about there isn't a deterministic relationship. It's not exact. So that means that there's going to be some kind of random component in the relationships that these variables have between them. So when we talk about linear regression, a simple linear regression model is going to be y, my dependent variable, equals beta sub 0, which is my unknown intercept parameter, plus beta sub 1, which is my unknown slope parameter, times my independent variable x, plus a random variable epsilon that's going to be assumed to be distributed with an expected value equal to 0 and a variance equal to sigma squared. Now, this equation should hopefully look familiar to you as the equation of a line plus this extra little epsilon deal. Now, an important aspect of regression analysis is estimating parameters. When we estimate those parameters, what we've done is we've formed a fitted regression line. So we have y hat equals b0 plus b sub 1 times x. B sub 0 is an estimate of the parameter beta sub 0, and b sub 1 is an estimate of the parameter beta sub 1. And y hat is my dependent variable, my estimate that I find doing this, and x is my independent variable. Now, every time we fit a model, every fitted model is going to have some kind of error. We call it a residual. So the residual, or the error in the fit, we can find that just by taking the true value of y and subtracting the estimated value of y for every y value in our regression data that we're given. Now you might be wondering, well, how do we estimate b sub 0 and b sub 1? Well, there are multiple ways that we can do that. One of the ways that we look at it is you can graphically do so by looking at a scatter plot or a scatter diagram where you plot all of the data points that you have, and then you can visually estimate what you believe the slope and the intercept to be for the line that goes through the data most accurately. Since just visually guessing what these parameters should be is not always the best estimate, we have a technique that we can actually calculate estimates for B1 and B0. When we do this, what we will have done is created the least squares fitted model. So you can see the formula there for B1. I'm not going to try to say it out loud because it's going to end up being a whirlwind of variables around you, but take a look at it. And then for B0, this is a lot easier because once we've found B1, we can use that and simply solve for B0. So you might find yourself asking, what's so great about this least squares estimate? Why should I go through the trouble of using that B1 equation especially? Well, the answer to that is what the least squares method does, or model does, is it minimizes the residuals. So if I take all of those vertical errors, what it's doing is it's minimizing what those vertical errors are in total for all of the data points.